ABB Power Systems. He's with our Power Systems Consulting Group based in Raleigh as well. He's got extensive experience in transmission planning and has managed and performed several studies involving the integration of large-scale wind projects in the U.S. And our last speaker, John Daniel, he's currently a senior principal consultant for ABB's Grid Systems and is principal investigator for the National Offshore Wind Energy Interconnection Study being funded by the U.S. Department of Energy. Just to highlight the key areas that ABB works in wind today. Again, this is an overview slide showing where ABB products and services are available. And again, this portion of the webinar, our first part, will be just focused on the Power Systems Consulting. But a key thing to highlight is we supply major electrical components to the turbine OEMs, all the way through to the developers of the EPCs. And basically from the time the wind comes into the turbine to the time it hits the grid, ABB's got major electrical components involved in that wind farm. Hopefully some of the key takeaways from today's webinar are being shown right now. But our thing that we're working on is maximizing the profitability. So how do you increase the benefits from a high-quality resource assessment campaign? Why production cost simulations can help firms understand the operational impacts to a wind farm and can ultimately affect system reliability and economics. How system impact studies help system planners understand the impact. And obviously how to prevent unexpected equipment damage and lost power output. So the key is careful upfront planning is very important, and that's what this seminar is going to highlight today. First speaker up, we'll have Dr. Michael Brower from AWS True Power.
Thanks very much. Wind power projects have been developed for several decades, and in the process of that, a lot of lessons have been learned and mistakes have been made. Over the last decade or so, this experience has coalesced into a fairly well-defined process that delivers quite consistent results for the energy assessment and assessment of the operational potential of wind projects. Of course, there's always uncertainty, and wind resources in particular are a significant source of uncertainty. But by following best practices in wind resource assessment and plant design, you can avoid the pitfalls and problems of past experience. The wind resource assessment process follows a number of stages that you see here. Starting very often with the early stage site prospecting, where you're looking for a suitable wind site. Then there is usually followed by a monitoring campaign with instrumented towers and other systems. There is data analysis and reporting, where the initial wind resource estimates are developed. And there's wind resource modeling, which extrapolates from where you measure to the rest of your site. And finally, you design your plant and perform energy production simulations. I'm going to go through each of these stages in quite briefly, but highlighting some of the key lessons learned from past experience. Next slide. Site prospecting involves a number of considerations. The first and probably most obvious is that developers are looking for a good wind resource. And that can be defined in a number of ways, but a typical definition is based on the mean wind speed. And these days, with the turbines that have been made available recently for low wind sites, a typical threshold for a viable wind project is around 6 meters per second. This kind of information can be gotten from wind maps, weather stations, and other kinds of information that are available when you don't already have measurements from a site. Another very important consideration is the transmission access and available capacity. Typical large-scale wind projects these days require a transmission interconnection of at least 115 kV. And in order to reduce transmission interconnection costs and risks, it's typical for projects to be within 20 kilometers of the existing grid. Other considerations include site constructability, slopes, road access, compatible land uses is very important, and rangeland and farmland are typically preferred. And finally, of course, developers look for sites where there are few or no environmental, community, or cultural kinds of obstacles. Next slide. One of the great new tools that have been developed in the last few years is online wind prospecting support. This is an example that our company, AWS True Power, has developed, and it's called the Wind Navigator System or Site Assessment Dashboard. And this shows you a wind resource map for an area of the central U.S. And in addition to just the color codes, which indicate mean wind speeds at a particular height, you can see, click on a location and get an estimate of the wind rose, which is the directional distribution, as well as the seasonal variation. And then if you subscribe to the service, you can get much more detailed reports, including estimates of the production from different turbine models that might be installed there. So it's a very good initial tool for finding sites. Next slide. A variety of site selection criteria can be included in a GIS, and this can provide a very powerful tool for screening large regions. This is an example here where in the background you see a wind resource map, and overlaid are transmission lines and boundaries of national parks or protected areas. And the outlines there are the result of a computer survey of the available sites which have identified particular areas with an associated rated capacity and likely capacity factor or mean energy production. Next slide, please. Now the next stage is to set up a monitoring campaign. Most monitoring campaigns rely still on tall towers, at least 60 meters in height. Although these days ground-based SODAR and LIDAR are growing in popularity because these technologies allow you to measure the wind speed to much greater heights, such as 200 meters. And tall turbines these days, their rotors span heights of up to 150 or 160 meters. SODAR and LIDAR work by bouncing sound or laser pulses off the atmosphere and looking at changes in the frequency due to the movement of the atmosphere. On a typical tall tower, you've got a variety of instruments. The mainstay are cup anemometers, which actually were developed over 100 years ago, but remain the primary instrument, as well as temperature and direction sensors like you see here. One of the important lessons learned from the past is that you shouldn't try to put your towers in the best locations in your, or what you suspect are the best locations, because this can lead to a bias in your assessment towards overestimating the windiness of your site. So what you really want is to represent the likely range of wind conditions that would be seen by turbines at this site. And it's very important to collect at least a year of data to reduce or eliminate the effect of the seasonality in the wind resource. So these are just some of the basic lessons learned, and developers who skip some of these steps or don't use the best practices can greatly increase the uncertainty in their assessments and produce big errors down the road. Next slide, please. This is just an image of a tall tower, a tubular tower being erected. Right now it's in its horizontal position so that the instruments can be mounted on it. You can see the guy wires, which are used to stabilize the tower. Excuse me. And please click for the animation. This is showing the same tower in nearly fully erect stage. It's winched up using the winch bar that you see there. It's a very simple process, requires a crew of 4 or 5 technicians for one of the large towers. Next slide, please. Now, after you start collecting data, then you need to make sure that the data are of good quality. And this is, although instruments these days are very good, significant problems can still occur, and you need to be very careful when you screen your data. Common data issues include sensor failures and degradation, icing in northern climates, and as well as tower shadow and secondary effects of towers. That image that you see there shows a CFD simulation of the effect of a tubular tower, the little circle in the middle, on the wind speed as it flows around the tower. And on the sides, there's an increase in the wind speed, and in front of and in back of the tower, there's a decrease in wind speed. So this is something that needs to be adjusted for or taken into account. Next slide, please. And this shows in a very graphic view of what can happen to real instruments in the field. On the right, you have a rather severe case of icing. This happens quite often in the winter in the U.S., in northern parts of the country. And it's something that needs to be detected and removed from the data. Next slide, please. After you've collected at least a year of data, then the next thing is to make sure that the period that you've collected is representative or is adjusted to a representative long-term period. The process is known as measure, correlate, and predict. The process is quite straightforward, although there are subtle issues that need to be considered. In the upper left graph that you see there, the blue line is the wind speed measured at your site, and the red line is the wind speed measured at some reference station, such as a weather station or the output of a weather model that is run over a number of years. So the idea is, as you see in the lower right, the data from the two locations are correlated in some way. Here there's a simple scatter plot with a linear fit, and that creates a model which connects the reference station speed to the site speed. And with that, you can predict or project backward in time to estimate what the long-term average conditions were at your site. The most important thing to consider, aside from the correlation, a high degree of correlation between your reference and the site, is that your reference needs to be a nice and consistent reference station. Any changes in the measurement height, the type of instrument, the location, and other problems can really play havoc with this process and introduce large errors. Next slide, please. Once you've measured and done your adjustments to the long term, you still may need to adjust to the hub height of your turbine. A 60-meter tower is tall, but modern large utility turbines have hub heights of 80 to 100 meters. And so that gap needs to be spanned by some kind of estimate. Now, ideally, if you have a SODAR or LiDAR, you can measure that directly. If you don't, then you need to extrapolate from your tower measurements. Extrapolation poses some risks. This is a rather extreme example that you see here, where the pink curve is the extrapolated wind speed profile from a tower that was measured at, I think, 30 and 50 meters height. And the blue line is the actual profile that was measured by a SODAR system. So you see in this case, the wind speeds actually did not increase nearly as much as you would expect from the measured profile at the tower itself. Next slide, please. After you measure the wind resource at a number of points and you estimate the hub height wind resource, then you need to consider how the wind resource varies across your terrain. And this serves a couple of important purposes. The first is just to be able to estimate the wind resource and energy production for each of the turbines at the site. And even more important, it allows you to optimize the plant layout. So you can use a computer program that we'll show you in a minute, which will allow you to maximize the energy production by moving turbines around at your site within the wind flow model and finding the configuration that produces the maximum energy production. Clearly, coming up with an accurate energy estimate in the end, which is critical for financing, requires that you do wind flow modeling well. There are a number of models out there, and they have a variety of characteristics which need to be considered for each site. Next slide, please. This shows you a typical output of a wind flow model run. This is just a wind map which has had the turbine locations overlaid on it. Additional information comes out of the wind flow modeling, including speed and direction distributions, as well as a time series of wind speed, direction, and temperature which is extrapolated from your measurements using a model. And all this information goes into your wind plant design. Next slide, please. In the final stage, we move into the energy assessment and project design. And this, of course, is a tremendously involved and complex process. Fortunately, some tools have been developed which make it much easier and more efficient, as well as much more powerful. The kind of software that we use is called OpenWind. It's a program that we developed in-house, and there's a free open source version of it as well as a commercial version. And there are several other packages out there which do more or less the same things. They basically allow you to design a layout and estimate and optimize and estimate the energy production from that layout. Some of the key inputs include a power curve, which defines the output of a turbine for a given input wind speed, a thrust curve and wake loss model. These determine how much the wind turbines influence the wind resource that's felt by other turbines. You see in the lower right there a picture, a very vivid picture of wakes produced by an offshore wind project. In this case, the increase in turbine behind each turbine has caused the water vapor to condense into droplets, and so you see a nice contrail behind each turbine. And finally, you can incorporate losses such as electrical, icing, and other environmental losses in your estimates. Next slide, please. As part of the design process, you need to consider a number of often competing goals, and it's sometimes very difficult to find a good balance, and different developers will have different priorities. One common goal is to maximize the rated capacity, which is basically the overall size of your investment and therefore the overall size of your potential cash flow. So you try to, in effect, you try to jam as many turbines into your land area as you can, but that runs up against another goal, which is to maximize the net capacity factor, which is the energy production per unit of rated capacity, and that's much more closely related to the cost of energy. So if if you put too many turbines in an area, then what happens is your wake losses go up, and that can then reduce your capacity factor. You also may have to put turbines in areas with less wind, and so you need to weigh that. Then there's cost of energy, which is important, and that comes into play when you look at the road layouts and cabling layouts that have to be built. And then of course, you have to respect all kinds of site constraints such as noise, boundaries, and so on. Now, finally, after all of this process, you can generate a large amount of interesting information. One type of information is a time series profile of the power production from your site, and this feeds into the kind of analysis that you'll be hearing about in a moment. You can look at the production cost of your wind project, revenues, and the impact on grid operation for a given wind project or for a collection of wind projects. So in this case, you see here a time series of plant production that's been simulated from the OpenWind model, and you also, in the lower right, there's a distribution of ramps or step changes in plant output, which can be an important consideration for grid planning and operation. Next slide. And lastly, just I realized that we had to cover a lot of ground in a short amount of time, and I would urge you to look at some of the references that are out there. This one provides a very good, in-depth, comprehensive overview of wind resource assessment practices, basically covering the range of topics that I addressed today. So there's some information here on this slide that where you could find this book. And thank you very much.
Thank you for that, Dr. Brower. Just a reminder for everyone, there's a question section on the webinar where you can submit your questions, and again, we'll try to get to those at the end of the seminar or the webinar. Next up, we've got Dr. Jin Zhu.
From the economic point of view, based on the analysis from the Michael's selection, we have two options to looking at the perspective from the wind farm developer point of view or from the operator point of view. We'll address both in the next in this presentation. Next slide. Okay. Site selection is we are looking at the based on the AWS true power analyzed result, we can decide what's the site capacity, energy can be produced, how much cost to develop this wind, and the transmission cost to deliver the wind to the connecting points. That's our selection criteria. Looking at the next slide, looking at this map, you can see this is it's a 1 month on-peak price signal, locational price signal, and you can look at here. There's some of the red line and the blue, red area and blue area. It's a contour map. It's based on the price. The red means the high price, the blue means low price. And the color change in location, it will be represent the constraint is limiting the flow. When we have a when we have the wind farm candidates here, they have onshore and offshore wind candidates. You can see which one you want to develop. You need to decide where you want to develop wind. You don't want to develop the wind at have a lot of transmission constraint area. That will be you will get the lower revenue for that purpose. And if you are looking at offshore wind, they are connecting to the high price, but they are developing costs, and it's more expensive. We need to find the compromise between the cost and the revenue, energy benefits. This is from the historical point of view. You can see this chart, but it's there's also a different point of view, looking at the future year and how will be changed. The color will be changed every month, every day, every hour. But it's how we can know where is the congestion, and this can be answered by using the production cost simulation model. Normally, we start with the energy velocity suite database. They provide the modeling data and also the historical information for us to benchmark with. And we also provide the simulation-ready database, and it's a good choice for you if you don't have your own benchmark database. The running simulation, you will be able to identify the transmission. When you put the new wind farm in, you will be identify the congestion pattern change. You will be calculate the wind curtailment, if any, happening to you, and calculate the energy revenue, decide your cost and revenue ratio. However, there's many other perspectives may change in the future, like the low gas price is not affect your wind generation profile, but does affect your revenue. So it will be this type of thing will be impact you. One of the lessons learned is one of the wind farm developer in the SPP, when the wind is built and into operation, they find there's more than sometimes it's 50% of the capacity they cannot deliver because of the transmission constraint, and they didn't look into what's the current transmission condition and the future transmission condition, what impact to their wind farm generation. So that could be avoided if you running this type of the model will be allow you to accurately to assess the impact on your revenue. Another thing I want to throw out here is watch out the market operation rule changed by the FERC rule. The FERC Order 1000 encourage the intermarket cooperation. Order 764 require intra-hour. That is good for the wind trading between the zone, between the control area. And also the 755 allowed the fast ramping devices developed. So those other rules will be impact on your revenue as well. Next slide is the wind farm impact to your system. There's two types of the impact. One is the system impact to you from the transmission congestion point of view. The other one is the wind plant impact to the system. Wind plants have a variable generation. They are not dispatchable, and they are sometimes out phase with the demand profile. They will increase the system reserve requirements and the ramping constraint. The forecasting error is bigger than the load, and also the base load thermal unit cycling caused by wind generation, because the wind generation is low at the off-peak hour. The base load unit's original design is the base load unit 100% loaded. Now it's because of wind, and they may only can operate in 40–50% of their generation capacity. That causes their cycling and impact their maintenance cost and the cause their cost increase. You may ask the question, why I care about the other people's impact? So, but the problem is that in the market system, the impact to the baseload units, they could be, for example, that the baseload units, they could be affect their maintenance costs and affect their reliability, false outage rate. Eventually they will be impact to the system reliability. The market operator will be responsible to that, will be address that by changing certain rules. One of the example, they maybe apply the ramping penalty to the system, and the wind, the ramping up and ramping down, they could be, you could be facing some kind of penalty to that. In addition to that, it's understand the wind operation. You also, from the perspective of utility and the market operator point of view, you will be doing some kind of the study. It's if the small wind farm comes to your system, you probably have nothing to need to be changed for the operation. But a bigger wind farm and larger penetration, you do need to watch out your system reliability and make sure you have a flexible reserve requirement for this variable generation. Some of the area, they define some kind of the new renewable zone that will be allowed to develop some policy-driven transmission expansion plan, which is unlock the barrier to develop the wind farm in the renewable zone. Recently, there's a lot of the studies going on in the WECC, looking at the energy imbalance market design. That benefit studies show that the EM not only able to provide improve the market efficiency, but also reduce the renewable curtailment, which is also you have a large territory to accommodate the large wind. It's the wind is the generation changing hourly, minutes in every minute. So we want to run not only single hourly simulation to assess the impact to the system. We also need to looking at the 5-minute interval or even 2-minute interval or 1-minute interval to looking at the wind impact to the system operation. Because of the ramping rate from the 5 minutes, the run will be much severe than you running hourly simulation. Those will be allow you to looking at the impact, how the ramping impact to the system operation. Another thing you maybe want to look out is because of the practices into the balance authority area, you need to control your interchange with neighbor for the hour also. You have fixed at the hour ahead, and you need to keep that. And the 5-minute interval will allow you to looking at the volatility of the wind generation and the impact to your LMP price. Because of your boundaries, you cannot share the risk to the neighbor system at that time within the hour. When you do the planning, economic planning for the wind, there's a major driver for the wind development is the production energy credit, the state renewable portfolio, emission policy, greenhouse gas policy will impact to the coal plants and will help us to generate a higher revenue. Renewable energy zone will allow us to deliver the power out of the zone because they have a policy-driven transmission development plan in place. So those are the major drivers. But so far we are looking at only the energy market. We are only looking at energy revenue. On the other hand, there's the other benefit we can looking at is called the capacity revenue. You can looking at the capacity value for your wind farm, and also choose the right technology of the wind turbine. You will be able to provide answer service as well. Improve the energy wind profile, working with energy storage, dispatchable hydro, and the plug-in hybrid electric vehicle will help the wind utilization and maximize your revenue. That concludes my presentation.
Thank you for that, Dr. Jinzhou. And again, just a reminder for the participants, if you have questions, please submit them online. We'll try to get them to them at the end of the session. Next up, we've got Dr. Plutla.
Thank you, Dennis. Good afternoon, everyone. The types of studies that Jinzhou talked about have to do with economics, revenues, market pricing, and curtailment. Now, in addition to the economic studies, technical studies are required by system planners to evaluate the impact of proposed wind farms on transmission systems and to identify mitigation to resolve adverse impacts. This slide lists typical studies that need to be performed to be able to interconnect wind farms into the transmission grid. Now, you know that transmission planners require these studies prior to granting approvals for interconnection and delivery service. Yes, these types of studies allow transmission planners to plan the system in such a way so as to reduce adverse impacts on their system. Now, if you're a transmission owner, the question you have to ask yourself is, are these studies enough to capture the impact of the wind farm on the system? Are there deficiencies in the planning process? If you're a wind developer, the question might be, do these studies protect my wind farm from operating risks, such as curtailment, loss of profit, etc.? Well, let's not answer this question right now. Instead, let's walk through the issues before answering these questions. Recent events have shown that there are gaps between anticipated and actual wind farm performance. Just to give you an example, we recently had a transmission owner come to us asking us why an existing wind farm on a system was tripping offline unexpectedly, even though studies showed no performance issues. Now, this wind farm was sitting at the end of a 62-mile long radial line, and after several rounds of discussions between the wind farm owner, transmission owner, and wind turbine generator manufacturer, it became clear that the wind farms were tripping because the system short circuit strength was not enough for the turbines to operate. Now, unfortunately, this requirement was not made clear when the developer bought the wind turbine generators. So what you have is, now you have this wind farm just sitting there, unable to generate power under certain system conditions, resulting in a significant loss of revenue. And the really unfortunate thing is the developer is being told that large system improvements will be required to allow the wind farm to operate on a continuous basis. It's basically a stranded investment. Now, in the great rush to integrate wind power, it looks like certain technical requirements were overlooked. I'm sure that somebody is sitting there wondering, why did this happen? We are seeing more event analysis type of studies to investigate performance issues, not seen in traditional system impact studies. And for wind developers, such types of studies are too late, which brings us to the question, can planning studies prevent problems before they happen? Are there deficiencies in the traditional types of studies? Well, planning studies can prevent these kinds of problems, but appropriate studies are needed in addition to the studies listed on the previous slide. Now, I know your developers are thinking, what, I just spent $200,000 on system studies, and now you're telling me more studies are required? Well, we are not pushing the idea of more studies for every wind farm. All we are saying is there may be situations where you have a wind farm connected to a weak system, or there may be series capacitors in the vicinity of the wind farms. So special studies may be required in such cases. Also, you want to make sure that the people who run these types of studies know what they're doing. Transmission studies expertise and equipment level expertise is what is needed to prevent issues like these. Some suggestions for wind developers, very often we find that wind developers embark on system studies without a sense of what type of wind turbine generator they would want to invest in their wind farms. This is not good practice. Our recommendation is that you choose your wind turbine generator early on in the game. This could potentially help save you money down the road in the form of costly system upgrades. You want to make sure that you hit the wind turbine generator vendor with questions such as these. Do the wind turbine generators require a certain minimum short circuit strength to operate? It's not the same as this question here. This second question is more of a system characteristic. So what you want to do is, once you get an answer from the wind turbine generator manufacturer, you want to take that answer back to the transmission owner and ask him whether his system can meet the minimum short circuit strength requirements of the wind turbine generators. Is the ramp rate controllable? Does it comply with grid code requirements? And I'm not talking here about fault right through. I'm talking about islanded systems, such as those in Hawaii or in Puerto Rico, that have stringent requirements, such as the ability of wind farms to regulate frequency and maybe to control ramp rates of the power. Models are critical. Aside from PSSE and PSLF models, ask the vendor if PSCAD models, EMTP type models are available. These may be needed for specialized studies. And if you're having trouble finding PSCAD models, talk to us. We are building up a library of PSCAD models for system studies. This slide may look scary at first, but the idea is not all wind turbine generators are created equal. This slide is from a study that we ran a couple of years ago for a transmission owner who was negotiating a power purchase agreement with a wind farm. And as is often the case, the developer did not choose the wind turbine generator prior to the study. Instead, he shortlisted 4 different vendors and wanted the TO's input on what performed best given the system limitations. Well, anyway, we ran the studies and found that each wind turbine generator impacted the system differently. What you're seeing here is voltage in the transmission system that's close to the wind farm, and there's a fault that plunges voltages down, and after the fault is cleared, voltages recover. And each of these curves is the response from different wind turbine generators. And the idea is to keep voltages above 80% of nominal. What we found is different wind turbine generators respond differently. There was only one turbine that passed the test. I like this slide because it illustrates the power of system studies. In this instance, the wind farm owner, transmission owner, used the results of our studies to influence the wind turbine generator vendor to make changes to the wind turbine generator ramp rates. If you look back at the last 10 years or so, you'll see that significant strides have been made in wind turbine generator designs. Power electronics have revolutionized the way wind turbine generators operate. And power electronics are also playing a role in the way transmission systems are designed. You might think that transmission owners are just building old-fashioned transmission lines. Well, the fact is they are utilizing advanced power technologies to maximize power transfer capabilities. I hesitate to use the term smart grid. It's not the grid that's smart. It's really the system planners, the engineers who design the advanced power electronics to make the grid more reliable. System operators, it's they who are smart. Anyway, the use of advanced power technologies is exemplified in the development of the ERCOT CREZ projects, which bring wind power from the Texas Panhandle to load centers in central and northern Texas. So what happened in the CREZ was the deployment of large amounts of shunt and series compensation to allow for increased power transfer capability. Several of these recommendations that were made in the studies are now coming to fruition. And there's a link here if you're interested in knowing more about the reactive compensation issues and the solutions that are available. I suggest that you read this report. Transmission owners with large amounts of wind on their system will find that the problems in their systems are very similar to what we encountered in the CREZ study. This slide was shown at the starting of the presentation. All I want to say is, aside from AC lines, FACTS, flexible AC transmission, as well as HVDC technologies are available to integrate wind. Energy storage solutions are being used on islanded systems to meet specific TO requirements with regard to frequency regulation. Our advice to transmission owners is don't be afraid to embrace new technologies. These solutions have been tried and tested. They have a successful track record. And there are fewer regulatory and environmental hurdles to clear than AC lines. Most importantly, don't underestimate the power of studies. They are a vital component of system planning. I just want to take a couple of minutes here by highlighting some suggestions for wind developers to make the study process as smooth as possible. We already touched on the first bullet, choose your wind turbine generator technology early on. I would also encourage wind developers to familiarize themselves with the grid code. Islanded systems have specific requirements with regard to, interconnection. Do your homework, perform due diligence to identify potential transmission system limitations from source to the sink. Every system is unique. Work with the transmission owners and ISOs to understand and work through the interconnection and delivery issues. Resolution of the impacts requires coordination between multiple parties, including wind generator manufacturers, generation developers, transmission owners, ISOs, and RTOs. Explore the concept of near-firm and non-firm transmission rights to identify periods when transmission capacity is available. And most importantly, think long-term. There's uncertainty everywhere. And you want to make sure that you can justify the return on your investment many years from now over the life of your wind farm. And this is the end of my presentation. Thank you for your time.
Thank you, Dr. Falula. Last up, we've got John Daniel.
All right. Thank you, Dennis. Everyone, let me take just a couple of minutes and very quickly go through a few considerations that you'll probably want to keep in mind A lot of the material that was in the earlier presentations considered sort of general evaluations that are applicable to almost all wind plants. But there are a few things that you'll want to keep in mind that are somewhat site-specific. So you'll want to ask yourself a few questions as you go through this planning process. Well, as you connect, what happens if you connect to a weak grid? Well, Sri touched on that a little bit, and we'll add a little bit to that. What happens if we connect a series capacitor? What happens if we're close to other wind plants or controlled equipment? Or if we're connecting from offshore, what happens if we have a very long cable? What might we want to keep in mind with that? For instance, with a weak grid, Sri brought this up, and he indicated that there was an example of a wind plant that had some difficulties because they were connected to at the end of a long transmission line, and in fact had a stranded investment. This result is becoming actually a bit more common. I just had a telephone call yesterday with a utility that has been working with a wind farm that's at the end of about a 60-mile transmission line, and they've had almost a year delay now in being able to move forward on some of their evaluations and moving forward towards bringing the wind plant online, specifically because they were close to a weak or they were at a weak point in the grid. Well, what's the problem with the weak grid? Essentially, it is that your wind plant may have some oscillatory behavior that is a detriment to the network, to the rest of the grid, and so the operator may curtail you and prevent you from being able to produce the wind that you want to. There are solutions for it. They tend to be rather costly. It may be something like extra transmission lines are necessary, or potentially a synchronous condenser might need to be added at the end, close to the location of the wind farms. These planning studies that were talked about by Dr. Palutla can be helpful in assessing any concern and identifying some mitigation measures. Next slide. Now, Dr. Palutla also mentioned that one of the things that can be done in the systems is to add series compensation. Put in a series capacitor in line with the transmission, and what that does is that it allows additional power to be transferred across a particular transmission corridor. And while it has that good benefit, it also has a side effect in that it can produce a phenomenon that has been called in various quarters self-excitation, SSR, or maybe SSCI. An example of it is shown in the figure that's there, and it's analogous to the feedback that you get from a speaker, but it's happening to the electric machine itself. And just as the feedback could potentially damage a speaker or the ears of the listener, so this type of feedback with the series capacitor has the potential of damaging the equipment that's on the transmission grid or within the wind plant. And if it doesn't, then it may cause the wind plant to trip offline, and either way you're not going to be able to produce the way that you would like. And then if it has this potential problem, it may even prevent the plant from being able to complete its interconnection. Now, the likelihood of this kind of a phenomena is dependent on the wind turbine type, the plant size, and where you interconnect. ERCOT, as part of their new planning studies, are going to be requiring studies for connections that are close to series compensation. And this is a prudent move because it can affect not only the transmission network, but to potentially other plants nearby. Fortunately, again, the risk can be assessed through some special studies, and the potential mitigation measures can be offered. A third planning consideration that you might want to ask yourself is, what if I connect close to other plants? Well, sometimes other plants don't play very nice. Of course, your plant will always be just fine, but what happens with the other guy, right? So you may be close to other wind plants. Thermal generators sometimes can have an adverse reaction to the wind plants. Or you may be connected close to a piece of equipment such as an SVC that has controls. Well, typically what winds up happening in this sort of a situation is that there's not a proper sharing of the voltage regulation of the system in the neighborhood. And what this usually requires is a slight adjustment to the equipment controls. Again, fortunately, they can be determined, the potential for this can be determined through some focused studies. And then finally, if you're connecting offshore in particular, you use undersea cables, one of the things that you'll want to ask yourself is, can we move our power? You see the graph up on the upper right. It shows the power transfer that is possible through cables of different voltage levels and at different distances from shore. The higher voltage levels start off at close range being able to transfer much more power than the lower voltage, but they also fall off much more quickly as you move out away from the shore. And all of this is caused by the high charging currents that reduce the capability of the cable to carry real power and transfer that to shore. It can be adjusted somewhat by reactors at one or both ends of the cables to help compensate for this capacitive charging that's taking place. But it may also require additional cables or a different voltage and will impact the upfront material costs for your plant. So we thought we would also bring these items to your attention so that you could keep them in mind as you're doing your planning for your wind farms. Thank you very much.
Okay, I apologize. We had a little technical difficulties there. Thank you, John. Just a summary slide for folks to review. And in essence of time, what I'd like to do is start taking some of the questions. We've got quite a few that come in. And again, if you have additional questions, please send them in on the bottom right-hand part of your screen. First question up, this goes to John, it looks like. John, you mentioned solutions for connecting to weak systems may be costly. What type of solutions can help address this?
Well, the main two solutions that are being considered are additional transmission into the area so that you increase the short circuit strength from the rest of the system. The second solution that is being considered and actually applied in some locations is placing synchronous condensers near the wind plants. These are basically big thermal generators that have their shaft cut off so that the only thing that they do produce is reactive power, but they contribute to the fault current capability of the network at that location and allow the wind plants to be able to operate in a much more stable manner.
Thanks, John. Next question that came in, this looks like it's more towards Sri. What recommendation do you have for wind farm developers who see all this uncertainty on the generation and transmission side and do not know for certain whether there will be a return on their investment, and can studies capture this uncertainty?
Ooh, that's a tough question. Yeah, I agree. There's a lot of uncertainty in the industry, particularly if you look at how transmission is evolving and how the generation scenarios are changing day by day. What system planners have been doing is they've been running scenario planning type of studies to look at the two bookends, if you will. There may be multiple bookends of system scenarios, and then run studies to kind of bookend the results of these studies, and then step back and make decisions in a way that are reasonable and acceptable across all these scenarios. We are seeing more of sensitivity studies being performed as part of system impact studies. What I would encourage developers to do is, don't be passive. You try to be more proactive. Get involved in studies. Read up, familiarize yourself with the issues, and insist on. Ask the tough questions to planners. Have they considered, the addition of so and so line, which is, maybe 2 years down the road and nobody knows. So scenario planning and sensitivity studies is the answer that will help, with the decision making.
Thank you, Sri. Unfortunately, I think that's going to be out of time for the questions. I'd like to thank everybody for attending today's webinar. Again, this was part one of a 4-part series that we'll be presenting this fall. When you close out the screen, there's a short survey of today's event. We would really appreciate your feedback and comments, and we will take those to heart. We will also submit answers to all the questions that were submitted out to the folks that got them. And again, you will have access to download the presentation from today as well. Also, you've got the contact information up on the screen. If there's anything that somebody said that you'd like to get more information on, please contact us directly. Thank you and have a great day.